Hello, today we reach lecture 14. In this lecture, we will continue our discussion on chapter 18, which talking about standing waves. But in particular, we will talk about the case when we create standing waves between having boundary conditions. So we will take that we have this string, for example, here of length L, okay, where it has two nodes at the ends because it is fixed at both ends. So consider a string of length L fixed at both ends. The standing wave is the superposition of the incident and the reflected wave. So let's assume that now we started having standing waves. What are the possibilities? It's either we have only one standing wave, or we have two standing waves, or we have three standing waves, or 4 or 5, etc. Okay, but the length of the string is kept constant, so the length of the string is kept constant. Now, if I have only n equal 1, that is, I only have one standing wave or one antinode. Okay, so let's say that n is number of antinodes. So if n is equal to 1, remember that the distance between two antinodes is lambda over 2, right? This we discussed last time. The distance between two antinodes is lambda over 2. Here, and also the distance between two nodes is lambda over 2, right? So what do I have here? I have one node over here and another node over here. So these are two nodes. These are two nodes. This is one node and this is another node. Okay, and this is also a node here. Now, the distance between them is lambda over 2. So the distance over here is lambda over 2. But also the distance is L, right? In this case, this means L is equal to lambda over 2, or we can say it in another way, that lambda is 2L. Lambda is 2L. Okay? This, we call it the fundamental first normal node. Okay? And here, if I am to write it in terms of a frequency, remember that V is lambda F. So V is lambda times F, which means F is V over lambda. So if I'm calling this lambda 1, then F1 is V over lambda 1. Remember that V is constant. It is not dependent on the string. It is depending on, it doesn't depend on V, on the frequency and lambda. Okay, so here I have F1 is 1V over 2L, and I have lambda equal to L. Now, what happens if I have if I have two standing waves? So here I can see here that I have two antinodes. So in this case, I have two antinodes. Okay, but I have three nodes, and the distance again between two nodes, so the distance which is from here to here, the distance from here to here is again lambda over 2. Okay, so I have lambda over 2 plus lambda over 2, which means I have 2 lambda over 2, that is lambda. I have lambda this time. So when I have two antinodes, I have the distance with this from here to here will be lambda, and lambda in this case is L, because also the distance from here to here is fixed, it's L. So I get lambda equal to L, or F2 equal V over lambda, which is 2V over 2L, which is 2F1. So I got F2 equal to F1. Now, if n is equal to 3, okay, if I have 3 antinodes, Again, the distance from here to here is lambda over 2. So I have lambda over 2 plus lambda over 2 plus lambda over 2 implies L, which is the distance from here to here, is equal to 3 lambda over 2, or lambda equal to L over 3. So I get F3, which is V over lambda 3, to be 3F1. Similarly, if I have 4 antinodes, I get lambda equal to L over 4, and I get F4 is equal 4F1. Now, the first case, when I have n is equal to 1, we call it fundamental first normal mode. When I have n is equal to 2, we call it second normal mode, and this is second harmonic. The third one will be third harmonic, and the fourth one is fourth harmonic, etc. Okay, fifth harmonic, sixth harmonic, etc. So, in general, standing wave on a string with 2 fixed ends, I have F1, that is the first normal mode, is V over 2L, that is 1 over 2L square root of T over mu, because V, if you remember, is square root of T over mu. So I wrote F in terms of T and mu, and Fn is NF1, that is n times F1, because remember F2 is 2F1, F3 is a 3F1, etc. So it is NV over 2L, that is N over 2L square root of T over mu. Okay, N is the number of antinodes, and it is the number of harmonics, and lambda N is 2L over N. So lambda 1 is 2L. Go back here. In the first case, lambda 1 is 2L. In the second case, lambda 2 is L. Then it is etc. Okay, lambda 3 will be 2L over 3, etc. Now note, the highest wavelength corresponding to n is equal to 1 gives us lambda maximum, which is 2L. So this is the highest wavelength we can achieve. It happens when n is equal to 1. Now, when n is equal to 1, we get the lowest frequency corresponding to F1, which is 1 over 2L square root of T over mu. Let's do some exercises. So we will start with this one from your booklet, number 27. In the arrangement shown in the figure below, an object can be hung from a string with linear mass density mu equal 0.002. So I have this mu, which we see in this formula, n over 2L square root T over mu. The string is connected to a vibrator with a constant frequency, so the frequency is not changing. So I have Fn is equal to F1. Okay, it is not changing. All the frequencies are constant, is the same. And the length of the string between point P and the pulley L, so I have L as well. They're giving me L. Okay, so I have mu, let's put it here, 0.002 kilogram per meter. I have L equal to meter, and I have frequency is constant. When the mass of the object is either 16 or 25, standing waves happen. So when I have M is equal to 16 kilogram, or M, so this is M1, or M2 is equal 25 kilogram, standing waves are observed. No standing waves are observed with any mass between these two values. Okay, so one of these will be referring to N, and the other will be N plus 1. And we have to decide which one is referring to N, that is, I have N antinodes, and which one, what does it mean that no other standing waves are observed? This means when I put here M1 equals 16, I saw, for example, 4 antinodes. When I increased the mass, I saw less antinodes. So if in case of M1, I saw 3, in case of M2, I will be seeing 2. Why is it when M increase M decrease. We're gonna show this together. When M increase and decrease. Why? Because I have V. I have V is equal square root of T over mu. Is equal to, I put this formula over here, it's equal to N over 2L square root of T over mu. Okay, but this is equal to constant. This F is equal to constant. Implies as T increase and decrease. Okay, because here F is constant and 2L is constant and mu is constant. So I have here M times square root of T. As T increase, so if the tension here is increasing and F is constant, N will decrease because N is what? It is F over square root of T. So as T increase and N will decrease. This is why when M increase, N decrease. Because tension here in the string is nothing but M times G. Okay, is this understood? So here the tension is M times G, which means as M increase, the tension will increase, but as tension increase, N decrease. Okay, so I have M1, let's say that M1 refers to N plus 1, and M2 refers to N. And now what do? We say frequency is equal to N over 2L square root of, so N refers to M2, so this is a square root of T2, which is 250 divided by mu, and this is equal to N plus 1 because F is constant over 2L square root of 160 over mu. So here I've just written this thing over here, that F is N over 2L square root T over mu. So I have at N, we said that M1 refers to N plus 1 and M2 refers to N. So when I put N, I put M2 over here, but times G, it becomes 250. And on the other side, I put N plus 1 for N. And for tension, I put M times G, which is 16 times 10, so it is 160 divided by mu. Now the frequency is constant, and here I can remove some terms because here 2L is 2L, so I can delete it. Mu is mu, I can delete it, and I will be left with N times square root of 250 equal N plus 1 times square root of 160, or N plus 1 divided by N is equal to square root of 250 divided by 160, and this gives how much? 250 divided by 160 square root of this. It gives 1.25. Now I do some math. Implies N plus 1 equal 1.25. N, I take N to the other side, so implies 1.25 N minus N. This gives us 0.25. N is equal to 1, implies N is equal to 4. So we found N. The question is, what is the frequency of the vibrator? Now, in order to calculate the frequency, I will just plug it in this formula. F is equal N, which is 4, divided by 2L. So let's do it over here in another color. So I will just put it here. Sorry, just let's put it here. F is equal N, which is 4, divided by 2L, and I have L is equal to 2, so this is 4 over 4, square root of tension. I'm using M, so I should use M2, which is 25, so I have 250 divided by mu, which is 0.002, and you get the answer to be 353 hertz. And here they are helping me. They said the greater the tension in the string, the smaller the number of notes in the standing wave. That is, they are telling me clearly that as T increase and decrease, okay? That is one, M increase and decrease. So it is helping me in the question, but we can also know it ourselves. Now, part B, let's do it here. What is the largest object mass for which standing waves could be observed? Remember, so we want the largest object mass. Remember, as mass increase and decrease, so if M is maximum, how much should N be? N should be minimum, which is 1. So I go to our equation, frequency is equal N over 2L, so I will put 1 over 4 times square root of tension, which is M maximum that I'm interested in, times 10 divided by mu, which is 0.002. And if the frequency is constant, we calculated it, it is a 353. So from here, if you just do the math, you will get mass is equal 400 kilograms. Okay, so how do we do the math here? I have here 1 over 4 square root of 10M over 0.002. The first thing, I get rid of the 4, so I multiply 353 by 4. Then I square both sides to get rid of the square root. Then I multiply by 0.002 to get rid of the denominator here. Then I divide by 10 to get the M. Okay, and by this we reach the end of this question. Let's do another one. You might notice that in the question I solved it a little bit differently. So this is just to give you 2 ways to solve the question. The second exercise, refer to the figure below where the attached mass M, again I have M here, hangs from a cord around a pulley with M is equal 5 kilogram. So we know that M is 5 kilogram. Okay. The length of the cord L is 2 meters. And the vibrator is set to a frequency of 15 hertz. So the frequency is also fixed. I have fixed frequency. Fixed frequency or constant frequency equal to 150 hertz. And a standing wave of 6 loops. So just as we see here, 1, 2, 3, 4, 5, 6. So we have 6 loops. Implies N is equal how much? The number of antinodes. I have 1, 2, 3, 4, 5, 6. So N is equal to 6. Remember this. So this is the 6th harmonic. Now, determine the linear mass density of the string. Okay, so here we start with this formula over here. So I have F. I will not put Fn over here because F is constant. So this is F equal N, which is 6, divided by 2L, which is 2 times L, which is 4, times square root of tension, which is m times g, so it is 5 times 10, so it is 50 divided by mu, okay? And instead of f, I will put my 150. And now how to solve this? So 150 is equal 6 divided by 4 is 1.5 square root of 50 divided by mu. So 150 divided by 1.5 is equal square root 50 over mu. 150 over 1.5 equal 100 equal square root of 50 by mu. I square both sides, so here I will have 100 times 100, so 10,000 equal 50 over mu, or 10,000 mu is equal to 50, and I get mu is equal to 50 over 10,000, which is 5 times 10 power minus 3, or 0.005. This is kilogram per meter. Okay. How many loops will result if the mass m is changed to 45 kilograms? So this is part A. Part B, the new mass is now 45 kilogram. Okay, and we want to find n if there is n. Okay, so again, we will be using the formula f is equal to n over 2l square root of t over mu, and I will plug the values. F is 150, n is our unknown, so it will remain 2l is 4 times square root of tension is mass times gravity, so it is 45 times 10, which is 450, divided by mu, which we have just calculated. And now I have 150 times 4 is equal n times square root of 450 divided by 5 e to the minus 3. So using the calculator, I get equal 300 times n. 150 times 4 is 600 equal 300 times n. So n is equal 600 over 300, which is 2 loops. So there are loops if we change the mass from 5 kilograms to 45 kilograms. Notice again that as we increase the mass, that is, as we increase the tension in the string, the number of loops were reduced from 6 to 2 in this case, from when we decreased the mass from 5 to 45. When we increased the mass from 5 to 45, we got less loops. And the last part, part C, how many loops, if any, will result if the mass is changed to 10 kilograms? So now we have m is equal to 10 kilograms. We will do exactly the same. So we will say 150. I will start immediately from here. 150 is this new n that I don't know, divided by 4 times square root of tension. In this case, it will be 100 divided by 5 e to the minus 3. So 150 times 4 equal n times square root of, or I can just get the number immediately. So 100 divided by 5 e to the minus 3 square root of answer. This will give 141.42. 150 times 4 divided by 141.42. We get n is equal to 4.24 is not an integer, implies no loops. Okay, so when we increased from 5 to 10 kilograms, we observed no loops. So I will stop here for today's lecture, and we continue this idea on Thursday. And if you have any questions, send me an email so as we discuss it on Thursday's live session. Bye.